In this video, we are going to talk about exponential form and complex numbers. And this video is kind of exciting for two reasons. I feel like we're now going to go beyond the stuff that you learned in algebra, maybe first year calculus, and learn some new things about complex numbers. And the second really exciting thing is this formula here, this e to the 2 pi I equals 1, is considered by many people to be the most elegant formula in mathematics because it contains the number e, pi, I, and then unity, 1. So it's these four powerful ideas, e, pi, I, and 1, all knit together in one formula. We are going to start by reviewing polar coordinates. So if you recall, if you have a vector, if you have a point in the plane, actually let's just say it's a point in the plane over here at the end of this vector, you can represent it by ordered pair, x and y. In rectangular coordinates, you would just put it as x, comma, y. But you can also represent this point by giving the radius and then the angle theta that this vector that represents the point xy, the angle that the vector makes with the x-axis. And here I have the formulas that convert from rectangular to polar and from polar to rectangular. So we'll review these polar coordinates, and then we'll go on and look at Euler's formula, which ties together e with cosine and sine. In particular, it's e to the I theta is equal to cosine theta plus I sine theta, and from there we'll derive this formula, z equals r e to the I theta. So a complex number now, not only can we express it as x plus I y, now in terms of polar coordinates, we're going to express our complex numbers in terms of r and theta. In particular, z is equal to r e to the I theta. And this is a very important way of expressing complex numbers that you should become very comfortable with. You'll see it all the way throughout this course here. Z equals r e to the I theta. And just a note, if r is equal to 1, the numbers e to the I theta lie on the unit circle. So theta can tell you exactly where that number is. So in other words, if here r is equal to 1 and you have e to the I theta, this theta tells you, well, first you know you're at radius 1, and then theta is the angle between the x-axis and then how far you're going to go counterclockwise. And in this case, we're going to go pi radians, and we're left at -1. So e to the I pi is equal to -1. If we have theta is equal to negative pi over 2, in other words, we have e to the I pi over 2, again, our radius is equal to 1. Since theta is negative, we're going to go in the clockwise direction by pi over 2 radians, and we end up at our y-axis is -1, but our y-axis is the imaginary axis, so this will be -1i or negative I. Over here, if we have theta, gosh, I have theta equals negative here and positive here, but I'm going counterclockwise, so this must be a positive. This must be an error here. But if I have theta is equal to, or if I have e to the I 4 pi, radius is 1, and theta is equal to 4 pi. So we're going to go around in the counterclockwise direction 4 pi radians. So here's 2 pi, and then here's 4 pi, and we end up at 1. So e to the I 4 pi is equal to 1. And last, we have our e to the 2 pi I. So here radius again is equal to 1. The 2 pi means we're going to go counterclockwise 2 pi radians, which gets us right back at 1. And we have our famous formula called Euler's formula, e to the 2 pi I equals 1. We also have one more formula, that z equals z naught plus r e to the I theta, where theta goes between 0 and 2 pi. This is the parametric equation of a circle with radius r centered at z naught. We will start by representing complex numbers in polar coordinates. So we have z, our complex number, is equal to x plus iy. So we can represent that in rectangular coordinates with x comma y. X on the x-axis, this is the real axis, the real portion of our complex number. And then y on our y-axis, this is the imaginary portion of our complex number. But we can also represent this in polar coordinates. In other words, we can identify this point by expressing or specifying how far we are from the origin, that's the radius, and then the angle theta between the positive x-axis and the vector that represents xy. From algebra, geometry, we know that the length of r, that is the distance from the origin now, is going to be the square root of x squared plus y squared. We also know from trigonometry that the tangent of theta, tangent is equal to opposite, so that'll be y over adjacent, that'll be x. We can also see, just for other reference, that cosine of theta, that's going to be x adjacent over hypotenuse, which is r, and sine of theta is opposite, that'll be y over the hypotenuse. These are what's going to help me then translate back and forth. So in polar coordinates, using this formula here, x will be equal to r cosine theta. Y is going to be equal to r sine theta. So z is equal to x, which is r cosine theta, plus I sine of theta. We also have theta now is the inverse tangent of y over x. And we have this convention of saying that we want this angle theta to be between negative pi and pi, because actually, technically, theta can be this, what we call our principal argument, plus any multiple of 2 pi. But we like to have our principal argument be between negative pi and pi. Here are the conversion formulas in summary. To go from rectangular coordinates to polar coordinates, we have r is equal to x squared plus y squared square rooted, and theta is equal to the inverse tangent of y over x. Let's use the convention where theta goes between negative pi and pi. And to convert from polar to rectangular coordinates, x is equal to r cosine theta, y is equal to r sine theta, and tangent of theta is equal to y over x. Oh, actually, I didn't need this. I only need x and y. Sorry, this was extra here. Bonus formulas. Now we have everything. Mostly this line here will help us derive this formula, which we will do next. But I'm just going to put the steps here where I have some more space. So we start off with Euler's formula, which is e to the I theta equals cosine theta plus I sine theta. That's this formula right here. And this formula you have seen before, probably in first year calculus. And we're not going to prove this formula, but just to say that this is a familiar formula relating e to sines and cosines. The next thing I'm going to do is look at our polar coordinates where we wrote z is equal to r cosine theta plus I sine theta. So I move this over here. Z is equal to r cosine theta plus I sine theta. Now here I have exactly the left-hand side of Euler's formula. So I can substitute e to the I theta for that. So now I have z is equal to r e to the I theta, which is exactly this formula here. And again, the importance of this formula here is that it allows us to write complex numbers in this exponential form, and we will use this constantly. So this is something you want to get really comfortable with, and also just know how it is derived. It comes from these polar coordinates, which again, we'll also use those constantly, and it comes from when you express z is equal to x plus iy, and you have this form, and then here you use Euler's formula to get z equals r e to the I theta. With this formula now, we can read off what the graphs of things look like really quickly. So if we have, let's just say radius is equal to 1 now. I mean, radius is equal to 2 just means it's the same angle, it's just that you're out at r equals 2. But let's just say radius is equal to 1, just so we can focus on the theta. So if we have e to the I pi, so what that means is we're at radius 1, and then theta is equal to pi. So we go around counterclockwise pi degrees, or pi radians, so we get to the point -1 on the real axis. So e to the I pi is equal to -1. The reason why you're going counterclockwise is because that's the direction of increasing radians, right? Usually you consider this 0, this is pi over 2, this is pi, 3 pi over 2, and then 2 pi. So now let's look at e to the minus I pi over 2. In this case, again, r is equal to 1, so we're going to be at radius equals 1, and our theta is minus pi over 2. So that means instead of going in the a counterclockwise direction. Since theta is negative, we're going to go in the clockwise direction, but only pi over 2 radians, and that gets us to this -1 on the y-axis. But remember, the y-axis is the imaginary axis, so this is minus I. Here we have pi is equal to negative pi over 4. I should put a negative in front of this pi. And so now it's negative, so again we're going to go counterclockwise. Our radius is equal to 1, and we're going to go counterclockwise 4 pi radians. So here's our first circle at 2 pi, our second circle at 4 pi, and we're at equal to 1, the real number 1. Last, we have e to the 2 pi I, and so since it's positive, we're going in the counterclockwise direction, in the direction of increasing radians. So here we go. Would be pi over 2, pi, 3 pi over 2, and then 2 pi, and we're at 1, the real number 1. So e to the 2 pi I equals 1. Again, we have this incredibly elegant formula that relates e pi I in unity 1. Something I want to mention about this example here, where we're spiraling around more than one circle. Actually, this whole time, your radius is always at 1. Even though I drew this smaller than 1, it's because I wanted to show the spiral. And actually, the way to think about this is you're spiraling at radius equals 1, but when you come around, it's kind of like you come up a level and you spiral. You're still at radius equals 1, but you've come up a level. So this is sort of like a, you're looking down like at a staircase, and the radius is equal to 1, but this is lower and this is higher, but the radius is still always 1 throughout this circle. And the last comment I have is the -1 squared. You know how you've learned in algebra -1 squared is equal to 1, but no one really gave you a reason. So you can look at this in terms of this complex number. So -1 is equal to e to the I pi. And if you square that, you'll get e to the 2 pi I, which is equal to 1. Next, we're going to look at this formula. Z equals z naught plus r e to the I theta, for theta goes from 0 to 2 pi, is the parametric equation of a circle with radius r centered at z naught. And I am going to start by moving this statement up here and cleaning out the other stuff so that I have some more space. And the first thing I want to explain, when we say it's parameterized equation of a circle, we're parameterizing by theta. In other words, we're letting theta range between 0 and 2 pi, plugging into this formula. And as we let theta range from 0 to 2 pi, we'll see that this formula will trace out a circle. We will start by looking at a simplified version of this equation here, and we're going to make z naught equal to the origin, 0, 0, and r equals 1. So then our z of theta is equal to 1 e to the I pi. And I'm going to put these notes. These are the things we had looked at before when we talked about the numbers e to the I pi lie on the unit circle, and then we just figured out, we used our theta to figure out exactly where on the unit circle we are. So this is for your reference. It's from the slide we did previously in this video. But now, as we trace out, let's start at theta equals 0. Oh, also the other thing I did to this graph, I kind of reminded you, along the positive x-axis, theta is equal to 0, or 2 pi, or other multiple of 2 pi. Along the positive y-axis, theta is equal to pi over 2, that's 90 degrees. Along the negative x-axis, theta is equal to pi, and then over here along the negative y-axis, theta is equal to 3 pi over 2. So I just labeled that for your reminder. When we start off with theta equals 0, because now, remember, here, theta is going to vary between 0 and 2 pi. So at theta equals 0, when we plug that in, here we're at radius 1, and at theta 0. As we go to theta equals pi over 2, we're going to get this point over here when we plug in pi over 2, e to the I pi over 2. And I think we hadn't done this as an example. We did negative pi over 2. But here we're going to go in the positive direction of increasing theta. So that means as theta goes from 0 to pi over 2, this z parameterized by theta is going to give us this quarter of the circle. Now as theta goes from pi over 2 to pi, z is going to parameterize this part of the circle, and then we continue on to 3 pi over 2, and then the 2 pi. So in this way, as we plug in different values of theta between 0 and 2 pi, we're going to trace out this circle of radius 1. Now I'm going to plug in r. I'm going to plug in a different r equals 2 just to see how that's going to affect our graph. And essentially it's just going to make the same circle but with radius equal 2. But z to the theta is now equal to 2 e to the I theta. So this gives we can read off the radius, we can read off the angle. As theta is at 0, we get this point here, we get the point 2. And as theta goes from 0 to pi over 2, wow, 2 somewhere over here, we're going to trace this arc of this circle. As we continue to theta equals pi, we'll trace this arc of this circle. This is kind of big, too big for my graph paper, but here we go. Here we have our r equals 2, so it just makes our circle bigger. For the last thing we're going to do is now we're going to make z equal a different point other than 0, 0, and I chose the point 1, 0, and I made the radius, I brought it back down to 1 just because here it was getting too big and I was running out of space. So now my z theta is equal to 1, 0 plus 1 e to the I theta. And what I did to start is I took my graph of 1 e to the I theta and I have it here in black. But now what this z naught equals 1, 0, it's going to shift all my points over by 1 in the x direction. So this point here gets shifted over 1 unit. This point here gets shifted over 1 unit. That was not 1 unit, that was 1.5. So this is 1, it should get shifted over 1 unit. This point here gets shifted over 1 unit, and this point here gets shifted over 1 unit. So as you can see, what the effect is it shifts the center of our circle to our 1, 0, which is exactly what our statement here said. So if we have z equals z naught plus r e to the I theta, this parameterization, and theta is what we're parameterizing by, that's the variable that we're letting range from 0 to 2 pi. The z will trace out a circle with radius r, just like here we had radius 2, centered at z naught, just like here we put z naught equals to 1, 0. Here z naught is equal to 0, 0. So that's what this statement is about. Now we've covered the main points of our video, but there are a couple of points that I should point out to you, couple of points that I should make. Going back to our polar coordinate representation of a complex number, so if z is equal to x plus iy, so in rectangular coordinates that would be the ordered pair x comma y, we can represent again our polar coordinates with the radius from the origin, that's r, and theta, the angle from the positive x-axis. So let r theta be the polar coordinates of the point xy that corresponds to z equals x plus iy. And we saw that this is equal to r cosine theta plus I sine theta, just plugging in our formulas for x and y into here, into x plus iy. Then r, which is the magnitude of z, is the length of the radius vector for z. It is never negative. That's the first point. And then theta, we had alluded to this before, is equal to inverse tangent of y over theta. So there are an infinite number of possible values for theta, including negative ones, that differ by multiples of 2 pi. So here our arg z is the set of all possible values of theta. And this capital arg z, that's our principal value. And it always varies between negative pi and pi. And so that's the one we're going to express it in. So here I've been labeling our axis of 0, pi over 2, pi, and then I say 3 pi over 2. But to get values between negative pi and pi, now we want 0, pi over 2, pi, and then negative pi over 2 here. So note when z is a negative real number, in other words, negative real number, it's along this line here, right? It's real, so it has no imaginary component, and it's negative. So along here, then z is equal to pi, not negative pi. I'm going to use the same example that we just did where we looked at negative 1 minus I, and we found that its principal component was negative 3 pi over 4. And I'm going to express now, I'm going to use this principal argument to express negative 1 minus I in this exponential form, which we had found, derived the formula earlier in this video to be z equals r e to the I theta. I've gone ahead and then written out what I'm going to do. I'm going to convert my z equals negative 1 minus I to exponential form. To put it in exponential form, I need to find r and theta, and actually we've already found theta, so really what we need is r. So r is equal to the square root of x squared plus y squared. In this case, x is equal to minus 1, so that's minus 1 squared, and the y is equal to minus 1. So what we get is square root of 2 for r. As I said, we already found theta over here is negative 3 pi over 4. So z equals negative 1 minus I in exponential form is equal to the radius r times e to the minus 3 pi over 4i. And technically, you can add 2 and pi, any integer times 2 pi to the 3 pi over 4 and still get z. But this would be our principal value, using our principal angle. Let's review what we have covered, and then I will have 2 more problems for you to try. So the first thing we did is we represented complex numbers using polar coordinates. So we can write complex numbers as x plus iy, which we can put in a rectangular coordinate plane. So if this is our vector representing the point xy, we go out along the x-axis x units and along the y-axis y units, and then we have our vector represent, or our point representation. We can also represent the same point using polar coordinates, where we use r to represent the radius, the distance from the origin to the point, and theta will be the angle formed between the positive x-axis and our vector. We have these formulas here, which allow us to convert from rectangular to polar and then polar to rectangular coordinates. Using these conversions, when we look at our x equals r cosine theta and y equals r sine theta, we can then write z is equal to x plus iy, which will give us an r cosine theta plus I sine theta. So here's how we can express z in terms of polar coordinates. We can go further and express this in exponential form using Euler's formula, which we had learned from first year calculus, which is e to the I theta is equal to cosine theta plus I sine theta. Now we replace this cosine theta plus I sine theta here with e to the I theta, and we get z equals r e to the I theta. And again, this is a very important way of being able to express our exponential form. This is also important as well as this. So you need to be able to be facile in all 3 expressions. The other thing about this theta, our theta, we want it to be, for our principal value of theta, we want to express theta, be able to express theta between negative pi, and we did examples of this. We talked about how once we have our complex number in this r e to the I theta, we can then quickly kind of plot out where it is, where our complex number is on the complex plane. We use r to give us our radius, and then our theta to tell us where we are, like how many radians to go out from the positive x-axis, and we have these examples here. We also did this last example to convert a complex number into exponential form. Here are 2 problems for you to try. So I will read through the problems. I suggest you stop the video, give them a try, and then come back and I will have solutions for you. So the first problem is to express z equals negative 1 minus 3i in exponential form over here. Watch your value for theta, as this vector is in the 3rd quadrant, the negative and the negative, and we want our theta to be between negative pi and pi. Second, express z equals 5e to the 2 pi over 3i in the a plus bi form. Pause the video, give them the problems a try, and when you come back, I will have solutions for you. Here are the solutions, and normally I just give you the solutions without going through it because a lot of the notes and the things we have at this point should not surprise you or be too new. But I do want to go through this example here because it does have a few steps when we're calculating theta. So in particular, I'm going to look at our theta calculation. And this is really important because later as the course progresses, you're going to have more complicated things. And this part here, writing it in exponential form, is the thing that you should be able to do without thinking a whole lot. And so the last thing you want to be doing is asking yourself, why is this negative 2 pi over 3 instead of pi over 3? So let's take a look at that. So I got this angle theta by using the inverse tangent of y over x. And my y value here is negative 3, so we're coming down negative 3. And my x value is negative 1, so we're coming over negative 1. So this is the angle here, this theta prime, from the negative x-axis over to my negative 1, negative pi over 3. This is the angle theta that we're measuring, and we get pi over 3. So this is pi over 3 from here. Again, because our numbers are negative 1 this way, negative square root of 3 this way. So this is the angle here, this theta. But if you recall, when we put in exponential form, we want to measure the angle from the positive x-axis. So we want to go from here all the way over. So we need to add these pi radians so we can get this full arc. And that's where this pi over 3 plus pi comes from, and I get 4 pi over 3. But now we are no longer in the principal argument where theta is between negative pi and pi. So what we want to do then is, once we're over here at 4 pi over 3, is we want to subtract 2 pi. So we're just kind of coming back around, but we get to the same vector, the same negative 1, negative 3. So 4 pi over 3 minus 2 pi gives us our negative 2 pi over 3, which is exactly this angle here, and also is between negative pi and pi. You always need to do these two steps. First add the pi, and then subtract, well, often subtract the negative 2 pi when you're in the third quadrant. That's it for this video. Thank you for watching.